All right. Today will be light, and we might finish quite early because it's just the last bit of the von der Mossberg network. And so I've already gone through the code last week. There were some bugs, but it's been sorted out, and so I'll kind of like recap the code and then talk a little bit, just very, very little bit about the, how do we evaluate the network. And then the rest of the time will be like more like lab, your own time, just like with the others, where we'll kind of free up open time for people to use the code or to mess around with it and then to evaluate it in your own way. I'm just going to give you some kind of initial, throw out some ideas there, and also to show you the past things that were done using this model on my own time previously. Okay, but before you dive into that, I just do some admin. So just to make sure that everyone's on track in terms of assignments. Okay, so assignment 2 should be due next week. If all goes well, if people need more time, just sound out, let me know, and I will, I have no issues with that. I think the last date that I need to submit your grades is sometime in the middle of June or towards the end of June. So we have some time to play with. Assignment 3, which is this von der Mossberg network implementation, which is, I've given you my Jupyter notebook code, so it shouldn't be too hard for you to implement it, right? You can copy it, but I hope that you can use it more like a guide and then try to kind of figure out your own way in your own modeling approach. My code may not be the most efficient. You can certainly make it more efficient than mine, okay? So that's one. But beyond that, the assignment 3 also, if you're up for the challenge, see if you can expand it. And that's part of what we will kind of have the opportunity. I'll give you some ideas later on, and if you can incorporate that into your assignment 3, that would really be beyond a doubt, no issues there, okay? And it can fail, it's fine. Okay, so that's in terms of the assignment. So I don't think anyone has problems with the homeworks, the first 2 tutorial homeworks. And then assignment 1, I think hot field generally, everyone's okay. And backprop, yeah, people are getting there. So the last assignment would be assignment 3, and you would have completed neural networks course, at least the basics here, okay? Any questions about so far the things that we've covered, all the models, any issues in terms of the coding that you guys have come across, or the assignments? No issues? Assignments okay? Or getting there? Okay? All right. So then the next admin would be, next week is 端午节, so we'll take a break, okay? And you can go and relax, or it'll be a bit of extra time for you to finish up all the assignments and coding and all that, all right? And after that will be the last class. We'll come back in the last class, and in the last class, it'll be kind of like I'll go through, like, in extension of this course in relation to the larger fields, the general neural network field, which is like including things like large language models, issues to do with these models, what other models there are out there beyond just the models that we have covered in class, okay? And I think it's kind of critical because here we get a basic understanding of how the kind of the heart of the neural networks here. But if you jump to most of the neural networks that are in use now in engineering, artificial intelligence in engineering, you'll be like, wow, they're so different. Their scale is so much, bigger and all that kind of stuff, okay? Where is the link? Is there a link even? And how is what we do relevant with that? Okay, so we'll cover issues, other issues they face the same as the issues we face, sort of, or rather the issues that we face are also faced by them as well. So we will talk about that, and I want to have it more of a discussion mode, the last class, all right? So I hope everyone can sort of come prepared with your questions and kind of like debate or discuss. I have my point of view, and I think everyone has their own point of view as well. And I think I don't want it, I mean, I can make it like a one-way thing, but I think it would be much more fun if everyone comes with their ideas and opinions about neural networks, okay? And I will probably, I've put up some pointers in terms of the things that we want to cover here. We will go through briefly what's a recurrent neural network, what's a convolutional neural network, the idea of exploding and diminishing gradients, especially in backpropagation, the problem of overfitting, and the solution, which is about regularization, okay? These are really big issues, and they are issues even in today's neural network, but it seems to be, well, we'll talk more about it. It's kind of interesting how large language models don't have as much problem of overfitting as compared to the smaller networks that we're using. So it appears that scale matters, okay? So, and that is also an interesting phenomenon, which we can discuss and talk about the implications. So I think the last class, I want to make it exciting and relaxing and interesting, you know, for more general, not just in terms of this course, okay? Yeah, and as I mentioned, there will be a visitor for that class, some teacher who is doing a project on English teaching will sit in the class as well, and it doesn't matter, you know, just treat her as a silent observer, or she might be able to participate, we'll see, okay? Yeah, that's just to let you guys know that there will be an extra guest during that time. And by that token, I hope you guys, beyond reading the Agarwal introductory chapter, you know, chapter 1, for the last class, I hope you guys can take some time to read chapter 2 and 3, because that will talk about the recurrent and deep neural networks and convolutional networks and some other expanded issues. Okay, then we can have more to discuss. And I would say that although this was, you know, a while back now, 2018, you know, about 8 years ago, it's still quite relevant because those are very fundamental issues. And if you want to make neural networks, or if you want to understand how neural networks work, and if you want to use neural networks, you kind of have to understand these problems, because otherwise you'll be implementing neural networks blindly and without thinking, and that's the worst thing you can do, because it's going to give you seemingly meaningful answers, as most of you would have known if you talk to ChatGPT or Gemini. Seemingly useful answers or sensible answers, but are just completely wrong. Or like you'd be stuck there and it's like, it says it works, why doesn't it work, or whatever. Case in point, I'm going to go through today the code and the bugs. Okay. All right, so that's the admin and the next couple of weeks as we round off into the summer period. Is everyone doing okay then in general? Is it getting too hot? I think it's getting too hot. So I'm ready to escape and go to summer break so that we don't have to deal with the heat. I don't know. Okay, the VDM Jupyter Colab bugs have been fixed. And this has been, we went through this last week, but let me have a quick recap. We have the modules that we are importing, which is the standard NumPy array and some plotly tools. And this is the key problem and the key fix, okay? Now, previously, hexagons, we have to deal with hexagons in VDM model. So what's a hexagon? We remember was about putting hexagonal quantized positions overlaid onto a Cartesian grid like the standard square grid that we use in normal human everyday life, right? So we have a hexagon manifold as well as a Cartesian grid manifold. Okay, it's a hexagon grid over a Cartesian grid. The problem was the way that you use so here you ask AI to generate a way to generate coordinates that are in hexagonal grid space. It did it in the old way being like the previous way, which is basically just the 3.5 of the size between the two centers and that's for the horizontal like length, and then the height is square root 3, okay? And actually it's the other way around. The width is square root 3 and the height is one half, because we were using the flat top like this. Like this, yeah, this is what actually what we're doing, okay? So it did this way, but it did it in a very weird way, because if you look at the code previously, I don't know if I still have it. Let me check if I still have it. Maybe I still have it, let's see. No, I deleted it. Guess it's too eager. Okay, never mind. Previously, what it would do is it would give you an x and a y coordinate, which is if you tell it how many rows of hexagons you want, how many columns of hexagons you want, it would generate the x coordinate for this hexagon point as, you know, square root 3 by 1.5 of the height and the row, okay? And then it would impose some sort of a scaling, like 0.75. I think if you guys have the old code, you'll see some 0.75 of the height, okay? Now, and in doing it, the way it did it, it basically made it so that the distances between the points, okay, like one point and this other point, the distances between these 2 points are no longer unit scale. All right, it basically, because it imposed some sort of a 75% scaling for one dimension, not the other, plus the way that it calculated it was like not taking into account the unit scale that I wanted. The spacing was 1, and what it did in that way was it's kind of like amplified the different the actual distances. So what essentially was, it visually looked like a hexagon, but underneath the numbers weren't really hexagonal. Okay, you can imagine how this can play out. How does that make sense? What was happening was, previously, okay, it was like something more like this. That, right? Oh, let's see, how do I do that? Okay, yeah. Previously, it was something more like this. So kind of like squashed, or I forgot it was squashed, or it could have been like this. You know, or maybe something like this, actually, yeah. Or stretched up like this, okay? In its implementation, it was doing something like this. So it's hexagonal in that, yes, oops. It's hexagonal in that it does have 6 sides and a centroid, right? And it sort of preserves this notion that this point and this point, right? This point, this centroid to this centroid is 1, okay? But the height and all that was not being adjusted in a systematic or in a correct way, okay? So what happened when you have this kind of problems? Well, when you calculate distance, remember, we care a lot about the radius, right? This radius is no longer like in a nice equidistant circular radius that we can use. One dimension, like say length or height, is associated with different unit distances because of the distortion. Okay? All right? So the previous method which was based on this, which makes sense because what you can do is it looks okay, but actually it calculates this, and then when you plot it, because the plotting can rescale things, right? You can squash the plot. You can say, please, when you plot this graph, make the width smaller and the height longer. You can stretch and scale the plot, right? But the underlying numbers are still wrong, correct? All right, so visually it looked like it was doing this nice grid on the left, on your left over there, yeah? But actually the underlying numbers were all messed up like this, okay? Now, this was because we used AI saying, hey AI, please generate a script that can plot hexagons on an XY coordinate for me. And said, oh yeah, because the website, this famous website, if you Google hexagonal grid, if you Google hexagonal grid, I'm going to wipe this out, yeah. If you Google hexagonal grid, this website pops up, Red Blob Games and all that, and it's read that, oh, if I want to generate X and Y's for a hexagonal system, this website tells me that I should do this height, right? And it did it. It implemented it in code. You see, then if you don't know what you're doing, you give yourself a whole lot of pain. And that's why when I used that, and I ran my learning thing. I thought my learning thing was a problem, right? And it took a while to figure out that it wasn't. The learning thing was actually okay because he had to go, there were no mistakes. So I went through all of it and like, no, everything is correct. Everything is correct. So where was the error? And the error came after doing some fault finding. I did some steps where I was able to plot this. What I did was I added in my learning training script this line here. Previously, this is part of my troubleshooting. I added weed in it. The weed is the distance between the weights of the excitatory to excitatory weights, the distances between those units rather, not the weights. Okay, the excitatory to excitatory units, the inter-unit distances. I added the fake hexagonal code was telling me those coordinates. So I added it in as I'm calculating the distance because remember, part of our von der Mausberg network requires to know which ones are the neighboring units based on their distances, right? So I logged it in so that I can spit it out as one of the outputs. And then I ran the code and I took a look at the output and you can see okay, in this case it's not so pretty, yeah. This is correct because now I did it correctly. Previously, do you know what the weights looked like? Basically, it was like one line and everything was flat or something. It basically doesn't look anything like that, which it should look like that, okay? Because what this is if you zoom in, okay? So unit 80 and itself, its distance is of course 0, okay? But unit 80 and 81, unit distance is 1. And then if you go further to, like all these distances, you can see, if you just go around it, okay? They're all within, like basically one unit, right, has a spread. So if you follow one unit, it has a kind of like a spread further and further away, right? Closest distance to further distance along one row. But then when you go up to the higher row, there's also still closer ones and then further ones, right? You can imagine for a single point, and as you go along every row, you get closer to further, closer to further, closer to further. That's why you get this pattern of repeating distances, because it's basically iterating through every row and every column. Okay, so there should be a, yeah, so like you can see this is fewer because the top rows are squashed in the hexagon, right? And then if you go to the next kind of block, it expands, 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 and then it shrinks again, right? It's a hexagon. So you can see that this geometrically, this is what that means, right? Okay, so previously the distances didn't look like that at all. So when I saw the distances, it was like, oh, no wonder the network was not behaving well, because when I was imposing the, the weights based on the distances were wrong in the first place. So I was imposing weights on the with the wrong criteria. So it was the distances that were wrong. And what made the distance wrong? So of course you wouldn't suspect the AI, right? AI is so intelligent. So I thought, oh, is it because the way that I'm calculating the distances, right? See, it brings you into this loop where you start doubting yourself. And spend a lot of time trying to kind of wait, is it because of my R to my Python thing, right? Because remember, I did this from R to Python, and I was like, wait, R does this, and then Python does this. And I tell you, that was such an irritating and frustrating thing, because nothing was wrong, everything was correct. And I was like, why is it not working? Everything here is correct. And then you start to wait, maybe the AI is not as smart. Finally, you should have suspected that right from the beginning. And yes, indeed, if you go back right to the beginning of the code where I said, this few lines previously, it was using this web pages or these kinds of things from what the AI was trained on to do that job that you asked it to do. It was doing what it knows to do based on the most popular websites or something like that. But what it should have done was to give you what you really wanted, was this approach. So I basically, in the end, I just said, well, I did it before, I calculated it, and I'll just do it myself. So this is purely my own, okay, and it's correct, all right? And I can tell you a little bit more about this if you're interested. The logic here is that, so if we have a hexagon state, a hexagon grid like this, and yeah, so there. The basis is like this. Basically, it looks like this, right? Vertices, okay? And I'm just going to move this out of the way for the moment. Okay, and then you change color. You have to note that this unit here is row 0, column 0. This unit here is row 0 still, column 1. Okay, in hexagonal coordinates. This is hexagonal coordinate like this. Okay? Okay? And then this one will be row 1, column 0, row 1, column 1, row 1, column 2, 1, 3, 1, 4, 1, 5, and 1, 6. Okay? Let's do one more row because I think it will come in handy. Let's do one more row. And this will be row 2, column 1, row 2, column 2 actually, row 2, column 4, and row 2, column 6. I might as well just, yeah. Okay. Okay, now the trick is to know that basically if I am in the hexagonal position, the hexagonal basis, then the distance, and I set my distance of the 2 units to be 1. Okay, let's say 1 cm or 1 mm or 1 unit, doesn't matter, just 1. Okay, then I want to know this one. let's say that this x and y for unit 0, 0 in hexagonal space. Okay, let's fix it so that in Cartesian space is also 0, 0. Okay, then the question is, if I were to make this 1, this distance is 1, then hexagonal unit 0, 2, what's the Cartesian coordinate? Okay, it'll also be 0, 2. Okay, but what is hexagonal unit? I'm going to write it here. 0, 1's coordinate. It's going to be 1. Sorry, 1. The x is 1. But what's the y? Okay. So in order for me to calculate, can you see this? Can you see this? If I were to do the red is the Cartesian coordinates. Okay? But here, what's the height? I know it is, the x is going to be 1, right? Because if this is 2, then this point is 1. Let's say whatever the unit scale of the two distances is just like arbitrary. That's why I set it to, so the unit here might be, in this case, is 2. You can just multiply it, right? You can just expand the scale. Do you all get it? It's a bit confusing. If the distances between 2 points, I set it to unit length, but the unit length is 2, okay, on the grid, then the half unit length is 1, right? Okay, and we know that this is going to be a equilateral triangle. Can you see? Okay, so trigonometry and geometry. Ooh, careful. You all right? Okay, so here the question is, what's the height? I know that the x coordinate of hexagonal point 0, 1, right, is somewhere, the x coordinate is in the middle of 0, 0 and 0, 2. Okay, but what's the height? What's the height? The height is then that's what this does. Okay, so if you recall, this theta is 60 degrees. It's an equilateral triangle. Okay, this is a right angle triangle. The length here is half of the size. Okay, so let's just make this S. Did I do it? Spacing, okay? And this will be half S. Correct? Does that make sense? Okay, so I can basically calculate this height. I want to know, I'm going to use green here. Okay, height, okay, is going to be equals to half spacing times tangent of theta in radians. Correct? This triangle here, I want to know the height. I know this I know, and I know theta, so I can calculate the opposite. So I know the height, and the height is going to be tangent of the theta in radians. So I have to convert the 60 degrees to radians, okay? And then multiply that by half of the adjacent length. Just basic trigonometry. Okay? Now, we meet with one problem, okay? So if we have this height, if you see the way I've done the coding, for x, no problem, right? Whatever the which column I'm talking about, okay? So like if I'm column 0, 0, then x is going to be 0, okay? And then because column is 0, r is 0, then x and y are 0, so no problem, okay? If column is 0 and row is 0, then x and y are 0, 0. So hexagon 0, 0 is also Cartesian 0, 0, no problem, okay? Now, let's do the case when x is, row is row 0, row is 0, but column is column 1. Okay? So spacing, half of spacing, right? Column 1 is half of spacing, so the x, this dimension, right? This length, right? Half of spacing. Okay? Sorry, it's a bit messy, but basically this is, we will know this, okay? But we are still in row 0, okay? And we know that the height is supposed to be this, the h value, right? So this h value, okay? But row is 0. So if I am hexagon unit 0, 1, my x is half spacing, but my height is, because of the hexagon problem, my height set to 0, although I know it should be the tangent property, the tangent amount, right? Okay, so that's why, so if you have to figure it out, so you realize that this is not going to work like that on its own. You need a contingency. If it is odd columns, which is column 1, column 3, column 5, you need to, whatever the y value is, you need to add you need to add the basic h tangent scaling unit for the height. In other words, you need to shift your basis up by half. All odd coordinates need to be shifted up by half, okay, relative to the hexagon basis. Okay, it's a bit tough to wrap your head around this. I mean, trust me, I spent a long time thinking about this also. But you go and think about it. You have to draw it yourself to figure out, like, if I'm on the even columns, no problem. X and Y, I can just use that formula, no problem. But if I'm on the odd hexagonal column coordinates, I have to include an offset. Okay? This is just because the rows of hexagonal bases do not distinguish between the Cartesian heights, which are different in Cartesian space, but they are all quantized to the same height, same row in hexagonal space. That's why for odd hexagonal units, you have to impose some offset. Okay? All right, so whatever this is, I have to figure it out, and therefore I ended up with this code here. So I'm going to clear that out. Okay? Yeah. So what I did in my code, fixed it, is to first compute the base property of the heights of a hexagon, half height actually, right, of a hexagon is equals to whatever spacing unit you want. You multiply that by the tangent of the 60 degrees in radians. So you have to use numpy degrees to radians first to convert 60 degrees to whatever radians this is. And I believe, does it give you the answer? No, it doesn't. Anyway, so 60 degrees, convert to radians. This results, feed it to tangent, then scale it by half of the unit spacing that you want. Gives you the base height. And then basically you use that to calculate the x and y of the hexagon. So this spits out the same thing, x and y coordinates of in Cartesian grid space of hexagonal units. And so I use this to feed it into the remaining plots and everything are all exactly the same. So there was nothing wrong with all the rest of the base code, okay? It was just that fixing that fixed everything, all right? And it spends you like 2 weeks to struggle with things that were already correct, and then it's the AI that's wrong, okay? It's the human that's correct here. All right, so let that be a lesson to people using ChatGPT and Gemini all the time, okay? All right, so then I won't go through the rest of the code, but basically because the rest of it is exactly the same, nothing changed from the last week. I guess the only change was that, well, yeah, I did add one change, which is, apart from this read part to see the distances, which is not really necessary, all right, because you already know the distances by theory, okay? But one other part I did add, and this was recommended by the AI. Where was it? Searching for it. Give me a second. Sorry. Yeah, here. Okay. So this part. Originally, we did NP sum of all the input to excitatory weights. This is for the normalization step, right? Originally, it was just to get the sum, the total sum of the weights first, and then use that as a way to kind of average every time the weights are changed, bring it back to the range of the sum. And I think AI was very not so happy with it for some reason. It recommended that I add this plus just this little teeny close to zero number. The reason is because it was afraid that if the sum sk is zero, somehow if the weights are zero, that this amount would have, to infinity kind of issues and end up being not defined, okay? So in order for that not to happen, never let sum sk to be zero. So just add some tiny little number so that it never gets to be that problem. I think that was just completely minimal advice, so whatever the AI did. So that's the only change there, and that's the reason. It's just so that things don't get to zero, that's all. Okay, and then I ran it, and then you can evaluate things like the heat map of the distances or the heat map of the weights. So this will be interesting. So let's take a look at the weights. See this? This is the heat map for the excitatory to excitatory units. So you can see now it's behaving correctly. So if I zoom in, okay, I'll zoom out a little bit. Okay, so for a given unit, it has weights set to 0.4 for its neighbors. Yeah? And the neighbors for a given unit, how many neighbors does it have? 6. Right? So you should count 1, 2, 3, 4, 5, 6 across one row, right? Every row should have only 6 0.4s, and everywhere else should be 0 along the row, and likewise the column. Does that make sense? Think about it, right? A given unit should have only 6 neighbors in a hexagonal, the basis that we have. And we ask the network, any unit that has an immediate neighbor in the excitatory layer, set that connection to 0.5 here, 0.4. We did it here. If the distance between unit 1 and unit 2 is equals to the E separation times spacing. Spacing is 1. EE separation is, EE separation is set to be order number 0. What is order number 0? Order number 0 is 1. Okay? So if the distance between these two units is unit distance, which is the next neighbor, then set it to P, and P is 0.4, which is the strength of the excitatory weights. Okay? So E to I to E is 0.3 and 0.286 respectively. So you can imagine. So this is 4, 0.4. So if I do I to E now, E to I now. Okay, this is a little different because you will see that it is not just 6 numbers, but there are 7 numbers, okay? So it's 1, 2, 3, 4, 5, 6, 7. So on one row, there are 7 instances of this 0.286, okay? It's because, oh wait, did I get it right? Should be Q, right? E to I should be 0.3. Oh, maybe that's another mistake. Q, let me see. E to I should be Q, and then I'll flip it later. But the numbers are so small, it doesn't make too much of a difference. Yeah, Q first, then R. I can flip it around later. Okay, so right now it's set to be R rather than Q. I should put this to be Q. I'll do it later. Q, R, okay? Yeah. So anyway, the values here are 7 numbers, and they are, right now, they are set to be R, which is 0.286, okay? And the reason is because we want the excitatory to link to the neighboring neurons, the neighboring units, so 6 of them, plus itself in the inhibitory layer. Okay, so then that becomes 7 units. So there's 7 weights here. And then finally, when we go from the inhibitory to the excitatory, okay, and you plot this out, you'll see it's a bit more fancy and complicated, right? But what it is a unit connects to its secondary neighbors, yeah? So there will be not just 6 now. How many is that? I think 8, or I can draw it out, okay? But a wider circumference, so more units, right? So you can see more units, and it's like further out. Okay? All right, so by looking at this, you can say that, my weights are set properly, okay? They seem to be making sense. Okay, and then, of course, you can see the input to the excitatory weights themselves, which we know is going to be more messy, not a constant, because those are the weights we update. We set it to be random, and then we update over learning. Okay, so we can say let's take a look at the initial, the very first instance, which is completely random. Okay? Well, it's not so random at the first round, because even the first round we already went through the 20 batch update at least one time already. Okay, but still not so clear pattern yet. So this is the weights at time 0. How about we trained it for 100 iterations? let's do the weights at time 30. Something clear coming out? Okay, then let's do the weights at time 99, which is the last one. Not much difference after 30 or 20, really, okay? What you notice is excitatory unit number 9, okay? And its relation to all the other units, okay, in the excitatory layer seems to be like I am the commander, okay? And then all the others have some more interesting variation, okay? Why? Take a look. Of all your stimuli, there is one place that is always on, isn't it? Right? It's the center. It's always on. Okay? And so if the center is always on, that unit feeding to the 169 is always on. Okay? Whereas the others are changing all the time. So there is at least one connection or one connection set that is going to be very, very reinforced over all the, super reinforced over all the training, and that is this one. This one. Okay? And it's no coincidence that it is sort of in the middle, because remember, and that's why the hexagon was essential, because there is no spatial bias. Every location is equidistant from every other location, and so that if it is the center unit that is always on, then we expect that it is the center location that's going to have this relationship to all other non-center locations. Okay? So it makes geometric sense as well. All right, so these are some, given the code works already, these are some evaluations you can do for the weights. You can go and plot the weights as a heat map over time. Okay? And I can add this as a kind of like a form here again. Use the nice trick here. And I'm going to add an element where add a form field. I'm going to put a slider. I'm going to say iteration 0 to 99. Okay, and I'm going to call this iteration. And I'm going to make it auto execute. Okay, so that I can go from iteration 0. Okay, let's play this movie. Iteration 0 to iteration 3, 9, 14. Not much change after, you can see. Just going deeper and deeper, that's all. Okay, because in other words, it's pretty stable after that. Okay, then I did the same thing for the excitatory layer output. Okay, so I have 9 input states, right? I have 9 orientations. So for orientation 1, at iteration 1, so at the first iteration, you see this pattern, an excitatory layer. Next one, okay? Try and hold this pattern in your brain if you can, okay? Look at that. So this is like the very, very first round of activity where the weights have not yet been fully trained, okay? You do see some clustering, but it is relatively, there's still some random dots, okay? Let's take a look. So hold this. This is pattern, the last pattern, okay? And this is at iteration 0. Let's look at iteration 99. Okay? Let's look at the other patterns. You don't get spurious dots. You do get edges, but you don't get spurious dots, or at least much fewer. Okay? And you can see the clusters sort of move around. Yeah? Okay, so this is a way to evaluate the model, okay? Visually at least, you can say that the model's sensitivity to a given orientation when it was untrained, and as training went from iteration 0 to iteration 100, and for all stimuli, all 9 stimuli. So you can use this way to visually inspect and see like if the model is behaving okay or not. All right? So, so you have the weights, you have the activity. So what are some other ways to evaluate? And this is something I'm still working on, but you can evaluate sensitivity curves. So I'm still working on it, but like I can give you the example here in the previous paper, which is you can ask, all right, after you have, at different stages of training, at run 1, at run 20, at run 100, okay, how many of those 169 units, okay, are only, are unimodal, means they only activate or are maximally active for one of the orientations, but not the others. Okay, unimodal. They like one, they don't like any others. Okay, how many are polymodal? They like maybe more than one. Okay, orientation, one orientation they'll activate, another orientation they'll also activate, you know, and maybe more than that. Okay, and how many basically don't activate? All right, so at run number 1, you get this kind of distribution. Okay. You can go and calculate it yourself. How do you do that? Well, you can count. There are 169, right? And maybe you target one neuron and then one unit, and you say, is it active for this stimuli? Is it also active for, so if you focus on, let's say, this upper left corner, this is active for, let's go back to 0 iteration. So it's not active for input state 0. It's active for 1. It's active for 2, so it's polymodal already. It's not active for 3. It's not active for 4. It's not active for 5, 6, 7, and 8. Well, it's polymodal because it was active for 2. Okay? So then you go through all 169, and then you count how many of them are active for more than one, for one only, or not active at all. Okay? So that will give you this table, right? And then you do it when the model has been trained for 20 rounds and for 100 rounds. You can see the number of unimodal units increases as you train, which is as expected, right? It becomes selective. So this is one evaluation you can do, okay? So I'm still working on that for this Python iteration. The other one is, just what I said just now was the maximal sensitivity, okay? You can flip it around and plot sensitivity curves. And what does that mean? It means that I can actually plot that here, like this. So I have the level of activity, the sum of the activity of this layer, okay, for the different kinds of inputs, all right? And then I can see like, for some inputs, though, that layer is most active or not active. So it's basically plotting what I just said. Is it polymodal or unimodal, but plotting it out as a line for like its activity for the different states, that's all, for a given unit, okay? So you can do it this way as well. So the table and these plots give you the same information, just one is numbers, one is graphical, okay? So you can do that. And then you can do layer entropy. Entropy is basically this. I think I need to go back how I calculate the entropy. Entropy is basically variability. So like if at run 1, the entropy is very high, so like over many times of you write the activity, remember we have to do it over many variations, right? So if the activity is fluctuating all the time, then the entropy is very high. But if the activity stays the same, remember right at the end the weights are kind of stable, it don't change just too much. So then the entropy is very low. So after run 20, the entropy is, very fast actually, right? At run 1 is high, but by run 20 you can see it doesn't change much between run 20 and run 50, which is what we saw just now. Kind of like it quickly dampened and it kind of stays still and doesn't change anymore. So the entropy is very stable after that. Okay? So that's another metric for like, is the network performing, in an optimal way or in a stable way. Okay? The best way to evaluate is to see it for yourself. So like you should see like at activation at run 1 without learning and the activation at run 100 after 100 learning runs. You can see that instead of a big patch and then small patches, kind of like messy, everything becomes very well self-organized, partitions, and equi-weighted. Okay? That is the characteristic we're looking for. All right? Let me see, what are these? Yeah, these are the same things. Okay, so this is just to demo the base implementation of the von der Morseberg. Okay, and I'm going to talk a little bit about some expansion ideas, and then after that we'll go for a break, and then it's like free time lab and all that for you guys to play around with the model. Okay, here are some ideas to think about. So, and this is what I kind of did. Okay, now we know that what we are doing here is we only have a 19-unit retinal patch. So it's like the whole of our visual system, what we are actually just modeling is, one point in space. And then we are asking how our visual cortex is sensitive to whatever orientation feature is in that one point in space. Okay? So, and we show that, there's these orientation selectivities or whatever to do with that one point in space. But what we can do, now that we know that, the brain, the visual system, can sort of pick up that there is either a vertical line, a horizontal line, or a slanting line, right, rotated line. What if we expand that and say like, let's make a shape, right? At the visual system, how do I test, how does it pick up or process not just one point in the orientation, but clearly we see more complex shape than that. So how does complex shape evolve, right? And if you think about it, complex shape requires not just one point in orientation. It requires a few points and their orientations together then you can make a shape. Otherwise, it's just a line, which is so-called shapeless, right? You need to have area in order to talk about shape. And area requires it not just being a 1D line, but kind of like a 2D area having different line combinations. Correct? That's the base definition of requiring a shape. So I asked, what if we expand the size of the retinal layers, and correspondingly, if there's more retinal layers, retinal patches, you might have a bigger cortical layer. Because why? When you do that, you can do this. Let's say this is a 19-unit patch. Let's say you don't have just one of them with orientation. Let's say you have like a diamond shape like this. 1, 2, 3, 4, 5, 6, 7, 8, 9 of them. Okay? And if you have 9 of them, and because they are hexagons, it's separated like this, but you can imagine if you squash them together, what you get is a cross here. And a cross can be in this location, or in this location, or a box. And it can be in this location, or in this location. Can you see? All right, I can make my input a bit more complex, not just 19 units, but 19 times 9 unit area. And then there are local orientations, and depending on how the orientations are, they make crosses or they make boxes. Iron can make more complex things if you want, fancy shapes. Then you can make bigger things. Okay, so if you do that, what kind of network do you need to process this? Oh, I had it at the top. To process this kind of input, well, I have 9 of the 19 units, right? You have to feed it, you have to give 169 fair chance. You have to also multiply by 9 at least, right? Repetition. So it'll be 169 but concatenated like this. And then maybe you might want to have an even higher layer, okay, that summarizes these patches. So this is now, and this one has its inhibitory, this one also has its inhibitory, okay? So you can imagine building a network like this. You can have expanded retinal input layer, expanded cortical layer, and a sort of a summary, deeper cortical layer or output layer. Okay? So think about that if you have these base components, whether you can do something like that. That is a challenge here. And that will be these 3 things. Expand the size of the retinal layer and correspondingly the cortical layers. Increase the depth of the cortical layer. So like input and output layer, or so on and so forth. And this last one, which has not been done, is like, to this point, we have fixed the EE and the IE and EI weights. Yeah? What if we let the network also learn those weights? Because neurally, that's also what happens also, right? Von der Mausberg fixed those weights because the question was, genetically predetermined instance, can we get self-organization still, okay? Just purely from the environmental dynamics. But what if we know that both are actually dynamically modulating? So what if we allow both freely, the degree of freedom to change as well, right? Will it work? I don't know, actually. We can try and we see. All right, so that's really it for me for the von der Mausberg model implementation. There's a lot of things still to do, a lot of things to try, okay? But that's part of it. The core and the heart is there. It works. You can use it. You can expand it and play with it as you want. Any questions about the implementation and the code? I can tell you the finding. I mean, I put this on the Git. So this is on the Git. Yep. Okay. So and equivalent references there. But I can tell you that the key finding for the expanded model was that these are some other details. The output layer had spatial encoding. It could encode like this cross or box was occurring in the top, which area of the visual field. Not surprising. It also had sort of how you say, at that level of the retina, it was not selective. It was sensitive to both kinds of shapes. So suggesting that if you want it to be more selective, you might need deeper layers. Or you might need to train it in a different way. Yeah. So the result of testing this model, okay, with these sorts of inputs, okay, led to the conclusion that that model can handle spatial locations, okay, object constancy at different locations, but it didn't discriminate between objects. It was just picking up that there were things happening in this location and things happening in that location. It didn't care about what that thing was so much, okay? And possibly, yeah, it suggests that you, to encode for that, you need deeper layers and you need different kinds of training, sure, okay? Okay, so any questions? One mouse board. Yes? Evaluate the model. Okay, so I had 3 ways I suggested. One was the, 4 ways. The first critical way is visual inspection, right? So you need to plot it like this so that you can say that at iteration 0, when you haven't really trained a model yet, and then you test the model for all the 9 different inputs, okay? You should see that the model is not yet very neatly clustered. There should be big patches, small patches, it's all very uneven, right? Is that okay? Is that part okay? Okay, so you have your train weights, right? Because the model, after you run the input, you give input to the model which you set up the architecture and the weights, right? It will output these activation of those excitatory layers. So activation state of excitatory layer at time t, that's ASET, okay? That's what is used to plot this. You should see this code, okay? ASET at iteration whatever for a given input state. If it is greater than the threshold, then set it to 1. If it is less than the threshold, then set it to 0, right? So that's what this is, 1s and 0s, okay? All right, so so that this is the pre-activation state, then this is the ReLU thresholding of the pre-activation state, right? So this is the first way of evaluating, using your eyes, okay? So it should be, as if you expect it to behave well, then it should be that at iteration, last iteration, that it should have nice clusters. And at the first iteration, it should have not so nice clusters, okay? That's one. The other one is to do this maximal sensitivity, which I haven't done it yet, but what it is you will get this table. Okay? You have 169 units in your excitatory layer, right? Okay? Then, and you know that you have just now the ASET for the 9 different input states, right? So you ask, you go back and you count. You focus, so the test is like this. Let's say at iteration 0, where it hasn't learned anything yet. Let's focus on this unit here. In fact, let's draw it out. Okay, let's look at that unit. Okay, you can count. Yeah, it's working? Yeah, okay. So it's on, okay, for state 0. It's off for state 1. It's off for state 2, 3, 4, 5. It's on for 6. 7 off. And 8 off. Okay? So it has 2 on and the rest are off. So this is a polymodal unit. This one unit, the red one, is polymodal. Okay? Then you go on to calculate this one. Do the same thing. How many times is it on? So if it is only on for one time, one input state, then it is a unimodal unit. If it is on for more than 2, more than 1, then it is polymodal. Okay? And some units are never on at all. Okay? Then it is just non-modal. Okay? So that's how you get these 3 numbers. in this table. Got it? Okay. Then you do it for iteration, say, 40. Okay? Then you do that again. Okay, so obviously you need code to do this. You're not going to do it by hand and calculate all the time. So you get then this set of numbers. And then you do it for 100. So you need this kind of parametric so you can see the trend. And you can see that basically at 20 already, you can see that the shape goes, it's already some unimodality earlier on, but it just basically increases, whereas the rest decreases. Okay? So you can see this trend, this pattern. Okay, so this, is that clear? Is that clear? Okay, so this is the second method. The third method is the sensitivity curves, which is this one, which is the same as the table. It's just basically plotting the table out. Where is it? Here. Yeah. So like for a given unit, I have 9 states or 8 states. I don't know why there's 8 here. But for a given unit, I can plot the ASET of that unit for the different states, right? So for this unit, right, I can say I can plot right? Maybe the state 0, 1, 2, 3, 4, 5, 6, 7, 8. So this is, it's not active here, but then not the binary state, the actual pre-activation state, okay? So this is going to be the pre-activation state. So then it's going to be like this, This was polymodal, right? So it's got at least 2 that is sort of like, and this is maybe theta, okay? Threshold, something like that, right? Okay, so it's the same thing. It's just graphically plotting it, that's all. So this is the other way. And then we have entropy. And entropy is basically, I think, to do with the, I need to go back, but I think it's to do with the weights over time. I think that one is okay because you can see that happening already. Like the weights kind of drop and then they kind of like remain stable over time. So I need to go back to see how I calculated entropy. And I think that's in my code somewhere. I haven't looked at it yet, okay? But entropy is variance, so which means like the deviation over time. If the deviation between this to this is keep flipping around, then the entropy is high. If the deviation from one to the other is small, then the entropy is low. Okay? So those are the ways to calculate. Okay? Is that help? Yeah. Any other questions? No? All good? All right. Well, I hope you guys are able to get these models, okay? Because I think they are very fun models and they are very fundamental models. And if you can use them, if you can implement them, you have a very good handle on. I mean, all those LLMs and all those, you can do that too. But if you can do this, you can do those. No problem. Seriously. Okay? I mean, you can do it without TensorFlow and PyTorch. You can do it just with NumPy. Yeah. You just need a lot of data, that's all. Like the whole internet kind of thing. I mean, that's how they did it before, and then they devised tools to make things more efficient, obviously, and easy. Yeah. All right? But at least the principle of it, you can implement it like this. Okay, so if no further questions, then I think that will be it for today's class proper. I'll open the next couple of hours is more for lab time for you to play the code. What I'm going to be working on is to do the evaluation scripts and tools, and I'll put it in the Jupyter notebook so you guys might be able to use it as well if you want to. Or feel free to do your own, generate your own and stuff like that. Okay? Next week is 端午节. We'll have a break, and then we'll see you the week after that. Okay? And I also open the time for if people have problems with the homework assignments or the whatever else at all you want to ask me, I'll be here. Okay? Until, what's the time? 10:30? Yeah, 10:40. Okay, I'll be here till 12-ish. Okay? All right. Okay, thanks, and we'll catch you in a couple of weeks.